Last time we discussed that an acceleration is caused by a push or by a pull. Today we will express this more quantitatively in three laws which are called Newton's laws. The first law really goes back to the first part of the 17th century, which was Galileo who expressed what he called the law of inertia. And I will read you this law. A body at rest remains at rest, and a body in motion continues to move at constant velocity along a straight line unless acted upon by an external force. And now I will read to you Newton's own words in his famous book, Principia. Every body perseveres in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. Now, Newton's first law is clearly against our daily experiences. Things that move don't move along a straight line and don't continue to move. And the reason is there's gravity. And there is another reason. Even if you remove gravity, then there is friction. There's air drag. And so things will always come to a halt. But we believe, though, that in the absence of any forces, indeed an object, if it had a certain velocity, would continue along a straight line forever and ever and ever. Now this law, this very fundamental law, does not hold in all reference frames. For instance, it doesn't hold in a reference frame which itself is being accelerated. Imagine that I accelerate myself right here. I either jump my horse, or I take my bicycle, or my motorcycle, or my car, and you see me being accelerated in this direction. And you sit there, and you say, aha, his velocity is changing. Therefore, according to the first law, there must be a force on him. And you say, hey there, do you feel that force? And I said, yeah, I do. I really feel that. I feel someone's pushing me. Consistent with the first law. Perfect. The first law works for you. Now I'm here. I'm being accelerated in this direction. And you all come towards me, being accelerated in this direction. I say, aha, the first law should work. So these people should feel a push. I say, hey there, do you feel the push? And you say, I feel nothing. There is no push, there is no pull. Therefore, the first law doesn't work from my frame of reference if I'm being accelerated towards you. So now comes the question, when does the first law work? Well, the first law works when the frame of reference is what we call an inertial frame of reference. And an inertial frame of reference would then be a frame in which there are no accelerations of any kind. Is that possible? Is 26100, is this lecture hall an inertial reference frame? For one, the Earth rotates about its own axis and 26100 goes with it. That gives you a centripetal acceleration. Number two, the Earth goes around the Sun. That gives it a centripetal acceleration, including the Earth, including you, including 26100. The Sun goes around the Milky Way, and you can go on and on. So clearly, 26100 is not an inertial reference frame. We can try to make an estimate on how large these accelerations are that we experience here in 26100. And let's start with the one that is due to the Earth rotation. So here's the Earth, rotating with angular velocity omega, and here is the equator, and the Earth has a certain radius. Radius of the Earth. This is the symbol for Earth. Now I know that 26100 is here, but let's just take the worst case that you're on the equator. You're there. You go around like this, and in order to do that, you need a centripetal acceleration, AC, which, as we have seen last time, equals omega square r. How large is that one? Well, the period of rotation for the Earth is 24 hours times 3600 seconds. So omega equals 2 pi divided by 24 times 3600, and that would then be in radians per second. And so you can calculate now what omega square r Earth is if you know that the radius of the Earth is about 6,400 kilometers. Make sure you convert this to meters, of course. And you will find then that the centripetal acceleration at the equator, which is the worst case, it's less here, is 0.034 meters per second squared. And this is way, way less. This is 300 times smaller than the gravitational acceleration that you experience here on Earth. And if we take the motion of the Earth around the sun, then it is an additional factor of 5 times lower. In other words, these accelerations, even though they're real and they can be measured easily with today's high-tech instrumentation, they are much, much lower than what we are used to, which is the gravitational acceleration. And therefore, in spite of these accelerations, we will accept this Hall as a reasonably good inertial frame of reference in which the first law then should hold. Can Newton's law be proven? The answer is no, because it's impossible to be sure that your reference frame is without any accelerations. Do we believe in this? Yes, we do. We believe in it since it is consistent within the uncertainty of the measurements with all experiments that have been done. Now we come to the second law, Newton's second law. I have a spring. Forget gravity for now, you can do this somewhere in outer space. This is the relaxed length of the spring, and I extend the spring. I extend it over a certain amount, certain distance, unimportant how much. And I know that when I do that, that there will be a pull, non-negotiable. I put a mass m1 here, and I measure the acceleration that this pull causes on this mass immediately after I release. I can measure that. So I measure an acceleration a1. Now I replace this object by mass m2, but the extension is the same. So the pull must be the same. The spring doesn't know what the mass is at the other end, right? So the pull is the same. I put m2 there, different mass, and I measure new acceleration a2. It is now an experimental fact that m1 a1 equals m2 a2. And this product, ma, we call the force. That is our definition of force. So the same pull on a 10 times larger mass would give a 10 times lower acceleration. The second law I will read to you. A force action on a body gives it an acceleration which is in the direction of the force. That's also important. Acceleration is in the direction of the force, and has a magnitude given by ma. Ma is the magnitude, and the direction is the direction of the force. And so now we will write this in all glorious detail. This is the second law by Newton. Perhaps the most important law in all of physics, but certainly in all of 801. F equals ma. The units of this force are kilograms times meters per second squared. In honor of the great man, we call that 1 Newton. Like the first law, the second law only holds in inertial reference frames. Can the second law be proven? No. Do we believe in it? Yes. Why do we believe in it? Because all experiments and all measurements within the uncertainty of the measurements are in agreement with the second law. Now you may object, and you may say, this is strange what you've been doing. How can you ever determine a mass if there is no force somewhere? Because if you want to determine the mass, maybe you put it on a scale. And when you put it on a scale to determine the mass, you make use of the gravitational force. So isn't that some kind of a circular argument that you're using? And the answer is no. I can be somewhere in outer space where there is no gravity. I have two pieces of cheese. They are identical in size. This is cheese without holes, by the way. They are identical in size. The sum of the two has double the mass of one. Mass is determined by how many molecules, how many atoms I have. I don't need gravity to have a relative scale of masses. So I can determine the relative scale of these masses without ever using a force. So this is a very legitimate way of checking up on the second law. Since all objects in this lecture hall and near Earth fall with the constant acceleration, which is g, we can write down that the gravitational force would be m times this acceleration g. I would normally write an a for it, but I make an exception now because of gravity. I call it gravitational force. And so you see that the gravitational force due to the Earth on a particular mass is linearly proportional with the mass. If the mass becomes 10 times larger, then the force due to gravity goes up by a factor of 10. Suppose I have here this softball in my hand. In the reference frame of 26100, we will accept to be an inertial reference frame. It's not being accelerated in our reference frame. That means the force on it must be 0. So here is that ball. And we know if it has mass m, which in this case is about half a kilogram, that there must be a force here, mg, which is about 5 Newton for half a kilogram. But the net force is 0. Therefore, it is very clear that I, Walter Lewin, must push up with a force from my hand onto the ball, which is about, of course, the same, which is exactly the same 5 newtons. Only now is there no acceleration. So I can write down that the force of Walter Lewin plus the force of gravity equals 0. Because it's a one-dimensional problem, you could say that the force of Walter Lewin equals minus mg. F equals ma. Notice that there is no statement made on velocity or speed. As long as you know f, and as long as you know m, a is uniquely specified. No information is needed on the speed. So that would mean if we take gravity and an object was falling down with 5 meters per second, that the law would hold. If it would fall down with 5,000 meters per second, it would also hold. Will it always hold? No. Once your speed approaches the speed of light, then Newtonian mechanics no longer works. Then you have to use Einstein's theory of special relativity. So this is only valid as long as we have speeds that are substantially smaller, say, than the speed of light. Now we come to Newton's third law. If one object exerts a force on another, the other exerts the same force in opposite direction on the one. I read it again. If one object exerts a force on another, the other exerts the same force in opposite direction on the one. And I normally summarize that as follows, the third law, as action equals minus reaction. And the minus sign indicates then that it opposes. So you sit on your seats, and you pull down on your seats because of gravity, and the seats will push back on you with the same force. Action equals minus reaction. I held the baseball in my hand. The baseball pushes on my hand with a certain force. I push on the baseball with the same force. I push against the wall with a certain force. The wall pushes back in the opposite direction with exactly the same force. The third law always holds. Whether the objects are moving or accelerated makes no difference. All moments in time, the force, we call it actually the contact force between two objects, one on the other is always the same as the other on one, but in the opposite direction. Let us work out a very simple example. We have an object which has a mass m1. This is object number 1. And m1 is 5 kilograms. And here, attached to it, is an object 2. And m2 equals 15 kilograms. There is a force. And the force is coming in from this direction. This is the force. And the magnitude of the force is 20 newtons. What is the acceleration of this system? F equals ma. Clearly, the mass is the sum of the two. This force acts on both. So we get m1 plus m2 times a. This is 20. This is 20. So a equals 1 meters per second squared in the same direction as f. So the whole system is being accelerated with 1 meters per second squared. Now watch me closely. Now I single out this object. Here it is.